Why do we explore space? Humans have always gazed at the starry sky with wonder and admiration. Since ancient times, our ancestors tried to find answers to the questions: who are we? Where does everything around us come from? Is there life beyond our planet? In the earliest civilizations, stars and planets became gods and symbols. The Egyptians aligned their pyramids with the stars, the Babylonians kept records of observations, and the Maya created a calendar based on the movement of celestial bodies. For them, the cosmos was not just a space, but a divine stage. In ancient Greece, philosophers made the first attempts to explain the universe rationally. Pythagoras spoke of the harmony of spheres. Aristotle created a model of the cosmos where the Earth was at the center and celestial bodies moved in perfect circles. Ptolemy systematized these ideas in the famous Almagest. However, only during the Renaissance did the understanding arise that the Earth is not the center of the universe. Copernicus proved the heliocentric model, and Galileo was the first two-pointed telescope at sky and sea mountains on the moons of Jupiter, and theses of Venus. These discoveries shook humanity's perception of its place in the cosmos. Exploring space became a symbol of human curiosity. From the first telescopes, we moved to spacecraft, artificial satellites, and interplanetary probes. In the 20th century, humans first set foot on the moon, and in the 21st, we are already preparing for flights to Mars. But the main reason why we explore space is not only the pursuit of new technologies or resources. It is the search for answers to questions. Are we alone? What is our future in the universe? And will we ever understand its true nature? The solar system or universe seems infinite, but the first step in understanding it is to study our own home. The solar system. At the center lies the sun, a medium-sized star that is the source of light and heat. Its energy is generated by nuclear fusion in its core, where hydrogen transforms into helium. The sun is so large that over 1 million Earths could fit inside it. Without it, life on our planet would be impossible. 8 planets orbit the sun, Mercury the closest. Small, scorching hot by day, but freezing at night. Venus, covered by a dense atmosphere of carbon dioxide, where surface sea temperatures exceed 450 degrees Celsius. Earth, our home, the only known planet with life. Mars, the red planet with ancient river valleys and polar caps. Jupiter, the largest planet, a giant with a massive storm called the Great Red Spot. Saturn, famous for its rings made of ice and rock. Uranus and Neptune, ice giants with methane-rich atmospheres, giving them a bluish tint. Beyond the planets, the solar system contains asteroids, comets, dwarf planets like Pluto, and countless moons. One of them, our moon, played a crucial role in human history. It controls tides, inspired poets and scientists, and became the first celestial body humans set foot on. The solar system is our cosmic backyard. By studying it, we not only better understand ourselves, but also gain keys to the mysteries of distant worlds. Asterisk stars and their life. When we look at the night sky, we see light that has traveled for millions of years before reaching our eyes. This light comes from stars, giant spheres of plasma shining thanks to nuclear fusion. Stars are born in clouds of gas and dust called nebulae. Under gravity, matter compresses and nuclear fusion begins. Thus, a new star is born. A star's life cycle depends on its mass. Stars like the sun live billions of years, eventually becoming radiants, then shedding their outer layers and leaving behind a white dwarf. Massive stars live faster and brighter. They explode as supernovae, creating elements that form planets and even us. The remnants of suck stars may become neutron stars or black holes. Interestingly, every atom in our body was once part of a star. We are literally made of stardust. This reminds us, when we look at the starisky, we see our own origins. Galaxies and dark matter, when we look up at the sky, we see only a tiny fragment of the grand picture. Stars do not exist alone. They group into giant systems called galaxies. Our home galaxy is the Milky Way. It has a spiral shape with several arms containing stars, planets, and gas clouds. The Sun is located on the outskirts of one of these arms, about 27,000 light years from the center. At the center of the Milky Way, modern data shows, lies a supermassive black hole called Sagittarius. Beyond our galaxy, there are billions of others. There are spiral, elliptical, and irregular galaxies. They form clusters, which in turn form superclusters, all creating a cosmic web. But astronomers noticed a strange fact. The observable mass cannot explain galaxies' rotation speeds. According to gravity, stars on the outskirts should move more slowly, but they orbit as if the galaxy contains unseen mass. This invisible substance was called dark matter. Dark matter does not emit light or interact with electromagnetic radiation. It can only be detected through its gravitational effects. Scientists believe that about 85% of all matter in the universe is dark. Without it, galaxies could not hold their structure. What is dark matter? Is it unknown particles we have yet to discover? Or do we need to rethink gravity itself? This is one of modern science's biggest questions still waiting for an answer. Cosmology, the beginning and evolution of the universe. Everything we see, stars, galaxies, planets, even space and time, has a beginning. Modern cosmology states that about 13.8 billion years ago, the Big Bang occurred. It was not an explosion in space, but the birth of space and time itself. At first, the universe was extremely hot and dense. In fractions of a second, it expanded rapidly, a process called inflation. After a few 100,000 years, the temperature dropped enough for hydrogen and helium atoms to form. At that moment, the cosmic microwave background radiation appeared, the faint echo of the Big Bang, which we can still measure today. Over time, gas clouds formed the first stars and galaxies. They create test structures we now observe. The universe is not static, it continues to expand. And astonishingly, the rate of expansion is increasing. This suggests the existence of another mysterious force, dark energy. What is the universe's future? Several scenarios exist. If dark energy remains constant, the universe will expand forever. If its strength increases, one day everything may be torn apart in a big rip. If dark energy disappears, the universe may stop expanding and collapsing, a big crunch. We do not yet know the answer, but by studying cosmology, we come closer to understanding where everything began and where it is heading. Black holes and event horizons, perhaps the most mysterious objects in the universe, are black holes. They form when a massive star explodes as a supernova, and its core collapses to a point of unimaginable density. A black hole has what is called an event horizon, the boundary beyond which nothing, not even light, can escape. That is why we cannot see a black hole directly, only its effect on nearby matter. Black holes come in various sizes. There are stellar black holes, the remnants of dying stars. There are also supermassive black holes hiding in the centers of galaxies, with masses millions or billions of times that of the Sun. One such black hole lies at the center of the Milky Way. In 2019, humanity captured the first image of a black hole, the shadow off the event horizon in the galaxy M87. This was made possible by a global network of telescopes. Another remarkable idea comes from Stephen Hawking. Black holes may slowly evaporate by emitting energy. If true, even they will eventually vanish. Black holes challenge our understanding of physics. They connect gravity, quantum mechanics, and thermodynamics. By studying them, we may uncover new laws of nature and learn how the universe itself works. Exoplanets and the search for life. Question: are we alone in the universe? Has always fascinated humanity. We seek its answer by studying exoplanets, planets orbiting their stars. The first confirmed discoveries of exoplanets occurred in the 1990s. Since then, the number of known worlds has exceeded 5,000, with new ones found each year. They are detected using different methods. Transit method: when a planet passes in front of its star, the light dims slightly. This reveals the planet's size and even its atmosphere. Radial velocity method: astronomers measure how a star wobbles under a planet's gravitational pull. Other methods include direct imaging. Special attention goes to habitable zone. Planets are worlds where temperatures allow liquid water. Water is key to life as we know it, but the search for life is not limited to exoplanets. In our solar system, there are candidates too. Beneath the ice of Europa, a moon off Jupiter, or Enceladus, a moon of Saturn. Subsurface oceans may exist. Today, programs like SETI attempt to detect radio signals from extraterrestrial civilizations. So far, no confirmed signals have been found, but even silence is an answer. Perhaps intelligent life is extremely rare. The search for life is not only a scientific mission, it is also a question about ourselves. Are we unique in this vast universe, or are rather other intelligent beings also seeking answers? Humanity's future in space. Humanity took its first steps into space less than a century ago. Yet today, we already talk about colonizing other planets. Mars is considered the most promising candidate. It has a day similar to Earth's, polar ice caps of water and usable resources. However, its atmosphere is too thin and temperatures are low. For humans to live there, we need new technologies, sealed dome cities, air purification systems, and radiation protection. Beyond Mars, settlements on the moon are considered a training ground for deeper missions. There are also proposals for next-generation space stations, massive rotating colonies where humans could live for years. For interstellar travel, even more revolutionary technologies are required: ion drives, nuclear reactors, or even concepts like a warp drive. Today, these sound like science fiction, but so once did the moon landing in the 19th century. Why does it matter? Because Earth is our home, but it is fragile. Asteroids, climate change, even cosmic time scales all remind us. If we want to survive long term, we must become an interplanetary species. Philosophical questions and conclusion. Exploring space is not only about science and technology, it is also philosophy. What does it mean for humanity to be part of such a vast universe? When we gaze at the night sky, we realize our smallness. Yet, at the same time, we are the only known beings capable of looking at the universe and trying to understand it. That makes us special. Space raises profound questions. Does our existence have meaning on the scale of galaxies? Is consciousness a unique phenomenon, or just one of many forms of intelligence in the universe? Will we ever grasp the true nature of reality? Perhaps answers will not come tomorrow or even in 100 years, but a journey to seek them is itself our greatest adventure. A lecture about space is not just about distant stars and galaxies. It is a story about us. We are part of the universe, made of its matter and energy. And our desire to explore space is our desire to understand ourselves. Space telescopes and observations. Since the time of Galileo's primitive telescopes, humanity has been striving to peer deeper into the universe. But Earth's atmosphere has always been a kind of barrier for observations. It scatters and absorbs part of the light, causes the twinkling of stars, and distorts images. That is why the idea of placing telescopes beyond the atmosphere was a natural step forward. Thus began the era of space telescopes, unique instruments that revealed the universe in a completely new way. The most famous of them became the Hubble Space Telescope. Launched in 1990, initially it suffered from optical problems, but after repairs it turned into a symbol of cosmic science. Thanks to Hubble, we obtained incredibly detailed images of distant galaxies, nebulae, and star clusters. Its iconic photos, like the pillars of creation in the Eagle Nebula, were not only scientific breakthroughs, but also cultural phenomena that inspired millions around the globe. Scientists use Hubble's data to measure the rate of cosmic expansion and refine the age of the universe. Yet astronomy is not limited to visible light. The cosmos radiates in different ranges: infrared, ultraviolet, X-rays, and gamma rays. Each opens its own picture of reality. For example, the Chandra X-ray Observatory reveals hot regions around black holes and neutron stars where temperatures reach millions of degrees. The Fermi Gamma Ray Space Telescope studies the most powerful explosions in the universe-gamma-ray bursts. A true milestone came with the launch of the James Webb Space Telescope in 2021. Its main task is infrared observation, which allows astronomers to see through dust clouds where stars and planets are born. With a 6.5-meter mirror, Webb is the largest and most powerful telescope ever built. It lets us look back billions of years in time to witness the birth of the first stars. It also studies the atmospheres of exoplanets, searching for potential signs of life such as water vapor or methane. Space telescopes are in many ways time machines. Because light from distant objects travels for millions or even billions of years before reaching us, we see them as they were in the distant past. Every image from Hubble or Webb is not just a view of space, but also a journey into cosmic history. Analyzing such data helps scientists reconstruct how the universe has evolved. The practical side of space astronomy is no less important. Observations of black holes, neutron stars, and supernovae give us insights into physics under extreme conditions that cannot be reproduced on Earth. Studying cosmic rays and gamma ray bursts allows us to test the fundamental laws of physics. Missions like Kepler and TESS, which USA transit method, have discovered thousands of new worlds beyond our solar system. The future promises even greater projects. The Athena X-ray Observatory, next-generation infrared missions to search for second Earths, and enormous orbital arrays that will work together as virtual telescope larger than Earth itself. Such tools may even allow us to study black hole event horizons with unprecedented detail. Space telescopes are humanity's eyes in the cosmos. They expand not only the limits of scientific knowledge, but also our worldview. Each new cosmic image reminds us we are a tiny part of a vast whole, yet capable of exploring the infinite. One day, these tools may even answer the ultimate question: are we alone in this immense universe? Magnetic fields and cosmic rays. Magnetic fields are invisible forces that shape the behavior of charged particles throughout the universe. On Earth, our magnetic field acts as a protective shield, deflecting high-energy particles streaming from the sun and from deep space. Without this magnetic cocoon, known as the magnetosphere, life as we know it would be impossible. Solar winds would strip away our atmosphere, and cosmic rays would bombard the surface with lethal radiation. Cosmic rays are highly energetic particles, often protons or atomic nuclei, accelerated to near light speeds by cataclysmic events such as supernova explosions, colliding neutron stars, or active galactic nuclei. When these rays hit Earth's atmosphere, they trigger showers of secondary particles that cascade toward the ground. Scientists study these cosmic messengers using detectors on the surface, underground, and even in space, trying to decode their origins. The story of cosmic rays is deeply tied to magnetic fields. Our sun has its own magnetic cycles that shape the flow of solar wind, which in turn interacts with Earth's field to create auroras near the poles. On larger scales, galaxies possess magnetic structures that can stretch for tens of thousands of light years, guiding cosmic rays across interstellar space. Even clusters of galaxies appear to be threaded with colossal magnetic fields, hinting that magnetism is a universal ingredient of cosmic evolution. For humanity, cosmic rays are a challenge as well as a clue. Astronauts traveling beyond Earth's protective field would be exposed to dangerous radiation levels. Shielding spacecraft and habitats from these energetic particles is one of the biggest obstacles to long-term spaceflight and colonization of other planets. At the same time, understanding cosmic rays may unlock the physics of the most violent cosmic accelerators, natural particle colliders, far beyond anything we can build on Earth. Magnetic fields also spark philosophical wonder. Though invisible, they shape the cosmos on every scale, from guiding star formation to protecting fragile life. Their study reminds us that the universe is full of hidden structures, unseen but essential, and that our survival depends on forces we barely notice. Gravitational waves in 2015, a century-old prediction of Albert Einstein, was confirmed. Gravitational waves exist. These ripples in the very fabric of space-time were first detected by the LIGO Observatory, created when two black holes collided over 1 billion light-years away. For the first time, humanity could listen to the universe, not just see it. Gravitational waves are produced by the acceleration of massive objects. When neutron stars spiral into each other, when black holes merge, even in the very first instance of the Big Bang, space-time itself vibrates. These vibrations stretch and squeeze distances as they pass through Earth, though the effect is unimaginably tiny fractions of Aperton's width. Detecting them requires some of the most precise instruments ever built. The discovery of gravitational waves has opened a new era in astronomy. While light, whether visible or in other wavelengths, can be absorbed or scattered, gravitational waves travel unimpeded across the cosmos. They carry direct information about catastrophic events hidden from ordinary telescopes. Already, detections of black hole and neutron star mergers shed light on how heavy elements like gold and platinum are forged in cosmic collisions. Future observatories, like the space-based LISA mission, will expand our hearing range into lower frequencies, revealing mergers of supermassive black holes and perhaps even echoes from the universe's earliest months. Gravitational wave astronomy is not just an addition to traditional observation, it is a revolution, giving us an entirely new sense with which to perceive reality. In listening to space-time itself, we are reminded that the cosmos is not static. It is alive with movement, rhythm, and echoes of ancient cosmic dances. Gravitational waves give us the chance to feel the heartbeat of the universe, Time dilation in space-time, which we often think of as universal and constant, is actually flexible. According to Einstein's theory of relativity, time flows differently depending on speed and gravity. This phenomenon, known as time dilation, is not just a theoretical curiosity, it is a measurable reality that affects astronauts, satellites, and potentially future spacefarers. When an object approaches the speed of light, its time slows relative to a stationary observer. Similarly, in strong gravitational fields, time also runs slower. Astronauts aboard the International Space Station, orbiting Earth at 28,000 kilometers per hour, experience time slightly differently than those on the ground. The effect is minuscule, but measurable with atomic clocks. For them, a few milliseconds are lost each year compared to people on Earth. The implications become profound near extreme objects, like black holes. A spacecraft orbiting close to a black hole's event horizon would experience minutes passing while years flow by for distant observers. Such scenarios, once thought purely science fiction, are grounded in solid physics. They force us to rethink our understanding of past, present, and future as fixed concepts. Time dilation also has practical applications. Global Positioning System (GPS) satellites must account for both gravitational and velocity based time shifts to provide accurate navigation on Earth. Without relativity, your smartphone's map would drift kilometers off course each day. Ultimately, time dilation reveals a deeper truth. Time is not an independent flow, but part of the fabric of space-time itself. Our journey into space is also a journey into the flexible nature of time, where seconds and centuries blur depending on where you stand in the cosmos. The Kuiper Belt and Oort cloud beyond Neptune lies a vast realm filled with icy remnants from the solar system's birth. This is the Kuiper Belt, a disc-shaped region populated by dwarf planets like Pluto, Haumea, and Makemake, as well as countless comets and frozen bodies. These objects are relics of the primordial disk of gas and dust that once surrounded the newborn sun. Studying them is like opening a time capsule from 4.5 billion years ago. But the Kuiper Belt is just the beginning. Far beyond, perhaps tens, oft thousands of astronomical units away, lies the hypothetical Oort cloud. This immense spherical shell of icy bodies may surround the solar system, extending halfway to the nearest star. It is believed to be the source of long-period comets that occasionally grace our skies. Traveling inward from the distant frontier after billions of years in cold storage, missions like New Horizons, which flew past Pluto in 2015 and later visited another Kuiper Belt object, have provided the first close-up glimpses of this mysterious region. They reveal complex geology, unexpected activity, and the possibility that even in such distant, frozen realms, intriguing chemistry takes place. The Kuiper Belt and Oort cloud remind us that the solar system is not neatly bounded at Neptune's orbit. Instead, it stretches into a vast frontier of frozen worlds, an edge that blurs into interstellar space. Exploring these distant zones may one day uncover the building blocks, off-planets, and perhaps even hints of how life's ingredients were delivered to Earth. The multiverse hypothesis: what if our universe is not the only one? This radical question lies at the heart of the multiverse hypothesis. Some versions of cosmology suggest that our cosmos may be just one bubble among countless others, each with its own laws of physics, constants, and histories. One version arises from inflation theory, which describes the rapid expansion of the universe moments after the Big Bang. Some models predict that inflation never ends everywhere at once, but continues eternally in different regions, spawning countless pocket universes. Another idea comes from quantum mechanics. Every possible outcome of a quantum event may generate its own universe, branching reality infinitely, while the multiverse remains unproven. It carries profound implications. If physical constants like gravity or the strength of electromagnetism in other universes, then most would be sterile and able to form galaxies, stars, or life. Yet in at least one universe, ours, conditions linked to make life possible. This idea, known as the Anthropic cycle, suggests that we observe this universe because only in such conditions could observers exist. The multiverse also stirs philosophical debates. If there are infinite universes, then somewhere may exist a version of you who made different choices. But can such universes ever interact? Can we ever test their existence? At present, the multiverse lies on the edge of science and speculation. Yet the possibility that our cosmos is just one among many continues to challenge our imagination of reality itself. Cosmic background radiation. The faint afterglow of the Big Bang still bathes the universe today, known as the cosmic microwave background (CMB). This radiation is the oldest light we can observe, released when the cosmos was just 380,000 years old. At that time, the universe cooled enough for atoms of hydrogen and helium to form, allowing light to travel freely through space for the first time. The CMB is astonishingly uniform across the sky. Yet tiny fluctuations, differences of a few millionths of a degree encode profound information. These ripples reflect the seeds of galaxies, imprinted by quantum fluctuations magnified during inflation. By mapping the CMB with missions like COBE, WMAP, and Planck, scientists have learned the age, composition, and geometry of the universe with remarkable precision. The CMB tells us that ordinary matter, everything we see, makes up less than 5% of the cosmos. Dark matter contributes about 27%, and the rest, nearly 68%, is the mysterious dark energy driving accelerated expansion. It also reveals that the universe is flat on large scales, a fact that continues to shape modern cosmology. For many, the CMB is a humbling picture, the earliest portrait of the universe we can capture. Looking at it is like seeing the baby photo of reality itself, frozen in time and carried across billions of years towards us. Space debris and human responsibility. As humanity expands into orbit, we are leaving behind a growing problem: space debris. Every rocket launch, satellite mission, or collision generates fragments that circle Earth at high speeds. Today, tens of thousands of tracked objects and millions of smaller, untracked pieces whiz around the planet, posing risks to spacecraft, satellites, and even the International Space Station. The danger is not theoretical. In 2009, a defunct Russian satellite collided with an active US satellite, creating thousands of new debris pieces. A single bolt-sized object, moving at 28,000 kilometers per hour, carries enough energy to destroy a spacecraft. Scientists worry about a chain reaction called the Kessler syndrome, where cascading galactions create so much debris that space becomes unusable. Managing this threat requires international cooperation. Some proposals include capturing debris with nets or harpoons, using lasers to nudge objects into decaying orbits, or designing satellites that can deorbit safely after their missions. But beyond technology, it requires responsibility. Space is not an infinite dumping ground. It is a shared resource that must be preserved for future generations. Space debris is a reminder that exploration comes with consequences. If we want to build a sustainable future among the stars, we must first learn to take care of the orbital neighborhood just above our heads. Terraforming concepts for humanity to truly become a multiplanetary species, we may need to reshape other worlds. Terraforming is the concept of transforming hostile environments into Earth-like habitats. The most discussed candidate is Mars, with its polar ice caps, 24-hour day, and traces of ancient rivers. But its thin atmosphere and cold climate pose enormous challenges. Proposed ideas include releasing greenhouse gases to warm the planet, building giant orbital mirrors to focus sunlight, or using nuclear explosions to melt polar ice. Others suggest genetically engineered microbes that could thicken the atmosphere over centuries. While these plans remain theoretical, they reflect serious thought about the distant future of humanity. Terraforming is not just about survival, it is about responsibility. Altering another world raises ethical questions. Should we reshape planets if they already harbor microbial life? Do we have the right top-leg god on a cosmic scale? Perhaps the first steps will be smaller, building domed habitats, underground bases, or space stations that mimic Earth's environment. Whether full terraforming ever happens, the dream itself pushes us to develop new technologies, rethink our place in nature, and imagine futures far beyond our planet. Cosmic art and inspiration. The cosmos is not only a subject of science, but also of art, philosophy, and imagination. From ancient myths about constellations to Van Gogh's Starry Night, the night sky has always inspired creativity. In the modern age, photographs from Hubble and Webb have become cultural icons. Their swirling nebulae and glowing galaxies rivaling the greatest masterpieces. Science fiction, too, reflects our fascination with the stars. Writers and filmmakers imagine alien civilizations, interstellar voyages, and cosmic destinies. These stories do more than entertain. They prepare you to think about possibilities, challenges, and meanings of space exploration. They inspire engineers to build rockets, scientists to search for exoplanets, and ordinary people to dream. Even music and poetry find resonance in space. The rhythm of pulsars, the silence of the void, and the beauty of starlight become metaphors for human longing. Space is a canvas on which we project our hopes and fears, our questions and our wonder. Ultimately, cosmic art reminds us that science and imagination are not separate. They are two ways of reaching for the same truth, that the universe is vast, mysterious, and deeply connected to our humanity. Looking at the stars, we do not only seek knowledge, we also seek meaning.